And in the hierarchy of aerospace metrics, thrust-to-weight ratio, or TWR, serves as the ultimate arbiter of engineering elegance. While chamber pressure defines the intensity of the fire, TWR defines the utility of the machine. To appreciate the Raptor 3 standing in this regard, one must view it through the lens of a world-class Olympic powerlifter specifically, one who weighs a mere 150 pounds, yet possesses the freakish, physics-defying ability to bench press a semi-truck. In the world of chemical rocketry, the Raptor 3 is that athlete, a lean, compact powerhouse that has stripped away every redundant gram of fat to maximize its muscle. In every kilogram of engine mass is a parasite. In the brutal calculus of the Tsiolkovsky rocket equation, engine mass is dead weight. It is a structural tax that must be paid in propellant every second the vehicle fights gravity. If an engine is too heavy, it becomes its own worst enemy, consuming the very delta V it was designed to provide. By achieving a TWR that eclipses any previous liquid-fueled engine, the Raptor 3 has effectively rewritten the cost-benefit analysis of heavy lift launch vehicles. And the architecture of Lean, from F1 to Raptor 3. To understand how far we have come, we must look back at the giants of the Apollo era. The Saturn V's F1 engine remains a marvel of 1960s engineering, producing a staggering 1.5 million pounds of thrust. However, the F1 was a massive, sprawling assembly of external plumbing, heavy steel manifolds, and a turbopump the size of a small car. It weighed approximately 8,400 kilograms, or 18,500 pounds, giving it a TWR of roughly 82 to 1. For its time, this was the pinnacle of performance. In the Raptor 3, by contrast, occupies a different paradigm. Despite producing roughly 280 tons of thrust, nearly double that of the Space Shuttle main engine, the RS-25, it does so within a footprint that is startlingly minimalist. By aggressively integrating components and utilizing the part deletion philosophy discussed in Chapter 3.4, SpaceX has driven the engine's mass down while simultaneously pushing its output up. The result is a thrust-to-weight ratio that reportedly exceeds 200 to 1. And in practical terms, this means the Raptor 3 is more than twice as mass efficient as the F1. If the F1 was a heavy-duty diesel engine for a freight ship, the Raptor 3 is a Formula One power unit engineered to the absolute limit of material capability, where every bolt and flange has been scrutinized for its right to exist. In the computer science of mass, performance per watt. For the graduate in computer science, the thrust-to-weight ratio of a rocket engine is the hardware equivalent of computational efficiency or performance per watt. In the realm of high-performance computing, it is not enough to have a processor that can perform trillions of operations per second if that processor requires a dedicated power plant and a room-sized cooling system to function. The true breakthrough occurs when you can pack that same compute density into a mobile chip. And in this analogy, the compute is the thrust, and the power or thermal overhead is the mass of the engine. A high thrust-to-weight ratio represents a reduction in the instruction overhead of the hardware. When SpaceX engineers removed the external sensors, the complex umbilical interfaces, and the secondary plumbing for hydraulic actuators, they were essentially refactoring the code of the engine. They moved from a monolithic architecture, where every subsystem is a separate, heavy module, to a microservices architecture, where functions are integrated directly into the kernel of the engine's 3D printed body. And by minimizing the hardware latency, which is the parasitic mass, the Raptor 3 ensures that the maximum amount of energy throughput, or chemical energy from methane and oxygen, is converted into useful output, which is acceleration. In a Starship stack featuring 33 engines on the Super Heavy booster, even a 5% reduction in individual engine mass translates into several tons of additional payload capacity. This is the difference between carrying a satellite and carrying a city-building module to the Martian surface. And the integrated manifold, and the death of plumbing, the primary driver of the Raptor 3 high TWR, is its radical approach to fluid management. In traditional engine designs, the path from the turbopump to the combustion chamber is a labyrinth of articulated pipes, expansion joints, and heavy flanges. These components are necessary to handle the vibration and thermal expansion of the engine, but they are incredibly heavy and represent hundreds of potential failure points. And the Raptor 3 eliminates this plumbing debt by utilizing internalized flow paths. Leveraging advanced additive manufacturing, known as direct metal laser sintering, SpaceX has moved the fluid channels inside the structural walls of the engine itself. This is akin to a biological organism, evolved to have its vascular system protected within its skeletal structure, rather than draped over its skin. And by turning the engine's skeleton into its veins, SpaceX achieves a dual-purpose structure. The metal that provides the structural rigidity to hold 350 bar of pressure is the same metal that guides the propellant. This functional integration is the secret to the Raptor's lean profile. When you remove the need for heavy steel bolts to hold separate pipes together, the mass of the engine drops precipitously. The result is a clean engine, one that looks more like a singular, sculpted piece of industrial art than a complex machine. In the gravity tax, why TWR dictates mission architecture. The significance of TWR is most acutely felt during the gravity loss phase of a launch. When a rocket sits on the pad, it must generate thrust greater than its own weight just to move. If a rocket has a TWR of 1.1, it is effectively using 90% of its energy just to hover, leaving only 10% for actual acceleration. And the high TWR of the Raptor 3 allows the Starship and Super Heavy to achieve a much higher initial acceleration. By getting the vehicle moving faster, earlier, it spends less time fighting the gravity tax of Earth's deep gravity well. This efficiency ripples through the entire mission profile. Lower gravity losses, faster ascent means less propellant is wasted supporting the weight of the rocket. Increased payload fraction. Every pound saved on the engine is a pound that can be added to the crew quarters or the fuel tanks. Enhanced reusability. For the Starship to perform its signature belly flop and landing flip maneuver, the engines must have a high TWR to provide the instantaneous, high torque thrust required to rotate a 100-ton spacecraft in seconds. And without the Raptor 3 specific power density, the Starship would be a paper tiger, a vehicle that looks impressive but lacks the thrust margin to carry meaningful cargo while retaining enough fuel for a vertical landing. The TWR is what transforms Starship from a theoretical concept into a viable freight train for the solar system. In material choice as a mass multiplier. Another critical factor in the Raptor 3 TWR is the strategic use of the SX500 super alloy. As discussed in the context of metallurgy, this alloy allows for thinner wall sections because of its superior strength at high temperatures. In the weight-saving phase of design, engineers often face a choice: use a lighter material like titanium that might melt, or a heavier material like steel that is safer. And SpaceX's development of proprietary alloys allowed them to cheat this trade-off. By creating a material that is both incredibly strong and heat-resistant, they could reduce the safety factor mass, the extra metal usually added to account for material degradation. In the Raptor 3, the material is the safety factor. The alloy's inherent properties allow the engine to be designed with zero margin thickness in non-critical areas, shedding kilograms without compromising the integrity of the 350-bar chamber. In the massive parallelism of 33 engines, the decision to use 33 engines on the Super Heavy booster is a direct consequence of the Raptor 3 TWR. In the past, engineers preferred fewer, larger engines like the N1's 30 engines, which famously failed. The logic was that more engines meant more complexity and more weight. However, the Raptor 3 high TWR and refactored design flipped this logic on its head. And because each engine is so light and self-contained, lacking the external rat's nest of sensors and wires, the complexity penalty of adding more engines is minimized. This allows for massive parallelism in the propulsion system. If one engine fails, the loss of total thrust is only 3%. If an F1 failed on the Saturn V, the mission was likely over. And this parallel architecture is only possible because the Raptor 3 is so weight efficient. If the engines were as heavy as the RS-25 or the F1, the booster's structural mass would have to be so thick to support them that the rocket would never leave the ground. The Raptor 3 TWR is the enabling technology for the multi-engine, rapid reuse philosophy that defines the SpaceX era. And the human element, designing for the machine that builds the machine. Finally, the TWR of the Raptor 3 is a reflection of design for manufacturability. A heavy engine with complex external plumbing is not just a flight liability, it is a manufacturing nightmare. It requires hundreds of technicians to manually weld pipes, check seals, and install sensors. And by simplifying the engine into a high TWR integrated unit, SpaceX has made the engine computable by robots. The reduction in mass is a byproduct of a design that is intended to be compiled by 3D printers and automated assembly lines. This leads to a virtuous cycle. A simpler design is a lighter design. A lighter design is a higher performing design, and a higher performing design is easier to mass produce. And the Raptor 3 is not just an engine, it is a standardized power module. By treating the engine as a commodity with a high performance-to-mass ratio, SpaceX can afford to lose engines during the testing phase, knowing that the code, which is the design, is solid, and the hardware is the most efficient version of itself that physics allows. And the final frontier of efficiency, as we move toward the next generation of propulsion, the Raptor 3 stands as the local maximum of chemical rocket efficiency. We have reached a point where further gains in TWR will require fundamental shifts in physics, perhaps moving beyond chemical combustion entirely. But for the era of liquid methane and oxygen, the Raptor 3 is the undisputed champion. It is the realization of the lean philosophy applied to the most violent machine ever built. And however, TWR only tells us how strong the engine is for its size. It doesn't tell us how thrifty it is with its fuel. A powerlifter might be able to lift a truck, but if they require 50,000 calories a day to do so, their range is limited. To understand how the Raptor 3 manages its fuel economy while maintaining this record-breaking thrust, we must turn our attention to the most sacred number in rocketry, the efficiency of the burn itself. This brings us to the final piece of the propulsion puzzle, the metric that determines whether a rocket can merely reach orbit or whether it can cross the void to another planet. 6.3 Specific Impulse, or ISP, the rocket scientist's MPG.